So today we start a discussion on the different implementation strategies for digital design, with reference in particular to complex integrated circuits such as microprocessors and the like. So there is a first observation to be done, and it is that chip complexity has grown faster than design productivity in the last, let's say, almost 40 years. Looking at the numbers from 1980, we observe what has been called the design gap. For example, the compound complexity growth rate, which is the average increase of the numbers of transistors per chip, has been of about 58% per year. Actually, it has not been constant, but I mean, looking at the sort of approximate compound growth, it is that number, 58% per year. On the other hand, the personal designer productivity growth rate has been on average in the same time of about 21% per year. So this is how do we measure the productivity of a designer? Let's say we measure the number of transistors that a single person can take care of, can design into, can put into a digital circuit per every month of work. So, of course, there is a significant difference between these two numbers. And the main result is that we have observed an increase of team size. This is, of course, obvious. You start from a small design. If you remember, I told you that the number of designers for the first microprocessor, the 4004, was 3, and in recent years, the typical team size for the design of a microprocessor is of the order of 1,000 people, okay, 1,000 designers. Of course, this is required in order to, let's say, compensate for this different growth rate. So, first observation, strong increase of the team size. Second observation, of course, we know where the complexity growth rate comes from. Basically, it comes from Moore's law, from the scaling laws that we have, the scaling of CMOS technology that we have already discussed. We have not discussed where the productivity growth rate comes from. Why it is possible that, let's say, designer can design more easily, can design more and more complex circuits. And actually, most of the productivity increase is due to the introduction of new design technologies from the 70s, the 80s, from the start of the era of design of microprocessors up to now. And actually, the various technologies that we have let's say, observed are shown here. Let's say we start from an era in the 70s when the 4004 was designed, which was an era in which everything was done by hand. Every circuit was designed transistor by transistor. Okay, also in the case of digital circuits. Then from the late 70s, we started to observe programmable logic arrays, which we we'll discuss in the next few minutes, and then standard cells, and then macro cells and module compilers, then gate array, and then reconfigurable hardware. So for the moment, these are just names. For you, I will show you in detail what's the meaning of those names. But let's say what is important in this moment is to understand that basically what happens here is that we have more and more software helping the design of more complex circuits. So with programmable logic arrays, we have a fixed hardware that can be configured or programmed in order to perform different combinatorial logical functions, and so on. Along this line, we see an increase in the complexity of the software that helps the reuse of hardware modules. Okay. Before we go in some more details in order to explain what these names mean, let's look at the general components of the complex integrated circuits. For example, microprocessors, but also special processor, digital signal processors are all in the same they all have the same general structures. We have four main blocks. We have a control block which is connected to the memory and to a data path. The data path is where we have all the combinatorial functions, the arithmetic operators, and then we have the memory, the control unit, and the data path unit that are connected to a block which takes care of input-output and to the interconnections with the external world. So all these different blocks have different types of circuits. For example, in the data path, as we mentioned, we have the combinatorial functions, and all the arithmetic operations are done in this region. And in this block, we typically require custom cells, which means digital blocks that are designed on purpose to work in the data path module. The control block, it is essentially a finite state machine which is built with standard cells. What are standard cells? Standard cells are reusable logic gates and single registers or single blocks of registers that can be, let's say, used as a standard building block of a combinatorial circuit of a finite state machine, so that each block is designed only once and then it is used in different types of more complex circuits. Okay. And essentially we're talking about logic gates and registers. Those are the main components of a finite state machine. Then we have memories, and memories are requiring very specific type of components. Of course, we can have different types of memories. I say here a memory block, but this block is formed by many different blocks, because of course we have read-only memories, we have readable and writable memories, Then we have memory with single port access, memory with multi-port access. Then we have different types of volatility of the memory. We have dynamic RAMs, static RAMs, non-volatile memories. And in this case, we have, as it is written there, regular macro cells. So typically, the building blocks of each type of memory are already designed, and they are available to form a larger memory block. And finally, we have the input-output circuits. And in this case, again, we need very specific components, which are buses and interconnects, and are typically usable by the designer as macro cells. They are macro in the sense that they are pretty large components, and they are very specific for this type of applications. And the main reason for that is that typically input-output components, since they have to communicate with the world that is outside the silicon chips, have to be able to have larger drive currents, because of course out of the chip everything is larger, we have larger capacitances, larger currents, and so also the blocks must be able to cope with that type of circuit. So the complex digital circuits, we have different main parts, main blocks, and each of those have different types of components. They can be standard cells, they can be specific macro cells. So in addition to the components, the other thing which is extremely important is how these components are connected. And we need to think about different aspects, because of course on the one hand one needs to connect the different components, the different blocks, and on the other hand one needs to provide a power supply and a clock signal to the different components. And these are difficult types of problems, and the way in which the problem is addressed for the various building blocks depend on the type of block. For example, in the case of memory and in the case of the interconnects and input-output circuits, we have typically a very regular structure. So also the interconnections are going to be extremely regular. In addition to that, a very specific aspect of the interconnect and input-output block is that from the external world we have the power supply and the clock distribution. So the power supply and the clock distribution comes from the external world and has to be distributed to all the blocks in the circuits. So we have very regular structure for this, very regular structure for the memory, and the clock and power distribution that comes from the external world through the interconnect and I/O block and has to be provided to all the elements of the circuit. In addition to that, we have the other two blocks that are much less regular. Now, I wrote that the control block is somewhat regular. As I mentioned, it is a finite state machine. And all the finite state machines typically have a pretty regular structure. On the other hand, and pretty similar from microprocessor to microprocessor, and the data path is on a relative basis much less regular than the control, because in the data path we have the specific operations and combinatorial functions so typically for each specific operation, for each specifically combinatorial function, we have the specific circuits. So also the interconnection is the interconnection between the different blocks is ad hoc for each particular function that has to be implemented. Okay. What is typically to be observed is that in the last 30-40 years, what has happened is that the placement of the various building blocks on the silicon chip and the routing, which means the design of the interconnections, is more and more automatic. So it was completely done by hand in the 70s, and now it's almost completely automatic. Typically, the design has only to check that the automatic placement of the blocks and of the interconnections is done properly. So, and is the use of this increasing set of software tools that has helped the designer increase its productivity in terms of transistor per month. Of course, this has had an effect also on the type of circuits, and in the sense that, of course, if we look at the image of a circuit as it evolves in time, we see that it becomes more and more regular because most of the design is done automatically. Just for example, this is the 4004, the first microprocessor. You can see, I've already shown this figure, but just to have an, let's say, just to see the image again, this had a little bit more than 2,000 transistors and was 3 by 4 millimeters in area. Okay, we already discussed some of the properties of this design. The important thing to notice here is that that all of the chip was done by hand, and you can see that it is very, let's say, unregular. We have two very regular regions, which are this one and the other one, that are most probably memory blocks inside, and the rest is, let's say, not regular at all. Okay. If you look at different and later designs by Intel, let's say this is a set of images. This is again the 4004. This is the 8080. This is the 8085, 8286, 8486. They are all pretty old, but you can see that the design becomes more and more regular. In this case, we have very regular structure here already in the 8085, which is from the early 80s. Okay, and then again, look at this region. Large blocks which are extremely regular, both in terms of the type of components and in terms of the interconnections, and also in this case is much more visible. Okay, so this is natural from some point of view, in the sense that of course when you increase the number of transistors, if most of these transistors are in a pretty regular array, it is easier to place them and to perform the design. Of course, because you have typical cells that are repeated again and again in the circuits. Okay. So this is pretty clear when one just look at the pictures. There's a transition from structures designed by hand to more and more regular structures. Okay, of course, there is a transition and the trade-off that we have between flexibility and efficiency. Let me just explain this thing in general. So one way of improving the productivity in the design is to reuse large parts of the hardware and then to program it to perform the functions that has to be performed in that particular case. So the huge advantage is that basically we can use a building block as it is. For example, a building block that has been designed for another application, we can take it and replace it in the new circuit. And then only by programming, for example, adapt the new hardware, the new old hardware to the new application. Okay. This is, of course, a huge advantage from the point of view of flexibility and of increase of the speed of design, because basically we already had the hardware, we just need to place it again. Okay, we already had the hardware, and in addition we know that the hardware is working. Okay, so from the point of view of productivity and of flexibility, this is a great advantage. It has a couple of disadvantages at least. The first disadvantage is that typically this reprogrammed hardware is less performing than a hardware fully designed for the application. Okay? This trade-off between flexibility and efficiency is very common. The other aspect, which is becoming more and more important, especially in recent years, is that typically, in addition to the loss of performance, we also have an increase of power consumption. So if we reuse a hardware and just reprogram it for the new task, we typically obtain something that also has a higher power consumption. Okay. As a general consideration, one can always think that consider that the more layers of software that you add to some hardware function, the higher the power consumption. Okay, so this is a very general consideration. One has to know that any flexibility and programmability of the functions has a cost in terms of performance and in terms of energy consumption. Of course, this thing can happen in different degrees. So we can have at the top of this scale some hardware that is completely custom for the application, which means hardware that is done once, that is fixed and cannot be modified after manufacturing. So no programmability at all. And this type of hardware gives you the least flexibility, as it is obvious, but also gives you the highest energy efficiency. Then by going down this scale, we can increase the flexibility and reduce the energy efficiency. The next step is what is called configurable hardware. So basically, it is hardware that has some parameters that can be changed by software. Typically, there are some, you can just imagine some digital hardware, for example, a microprocessor or a specific graphic processor. It is a completely general concept that has some parameters that are usually present in the memory that can be, of course, altered and changed by the designer. Of course, this adds a bit of flexibility because the parameters can be changed. Typically, they are written in a memory that is read at the beginning by the digital circuit. And typically, also, this is already a loss in energy efficiency. If we want to add some more flexibility, we can have an application-specific microprocessor. Sorry, I mentioned a microprocessor here. It's not yet the case. It's in the case of configurable hardware, you should not think about a microprocessor. You should think about something, for example, a digital filter or a digital filter probably is the simplest possible case, or let's say a digital circuit that has to take data from a sensor, for example. Or we can add some more flexibility using an application-specific microprocessor, for example, in this case, a digital signal processor or a graphic processing unit. In this case, it's clear that we add some flexibility because, for example, if we need to process some graphics, the GPU has some specific hardware for doing that applications, but also allows you to write a code that uses this specific hardware, and then you have a lot of flexibility in what you can use. Again, with respect to a custom hardware or a configurable hardware, using an application-specific processor gives you this loss in energy efficiency, which is still significant. And then finally, you have a completely general embedded microprocessor that, of course, provides you with the highest degree of flexibility, but it is also terrible from the point of view of energy efficiency. It's useful in this case to think in terms of a simple example. Suppose that you want to have a video codec. You want to implement a video codec. You can do it with a custom hardware, or with a custom hardware with configurable parameters, or with a DSP, or again with an embedded microprocessor. So all the four possibilities are available. Of course, the custom hardware, if you want to change the slightest thing in the algorithm of the codec, is not working anymore. So you have the least flexibility of all the different solutions. But of course, you really have the highest efficiency in terms of energy consumption. And looking at from a quantitative point of view, it's very useful to think in terms of degrees of orders of magnitude. Typically, from the point of view of energy consumption, you have something like this. You increase by 1 order of magnitude for each step along this line. Okay. If we consider this type of solutions, there's also an additional consideration that has to be done, which is related to the cost of an integrated circuit. Because of course the costs change a lot depending on the type of solution. So if we want to consider the cost of an integrated circuit, we have to split the cost into components. We have recurring expenses and we have non-recurring expenses. The recurring expenses are the so-called variable costs, and essentially to say the thing is in the simplest way, the recurring expenses are the expenses that are proportional to the sales volume. So they are proportional to the expenses that you have for each additional chip that you make. And then in addition to that, we have the so-called non-recurring expenses, which are also called the fixed costs. And for simplicity, we can say that the fixed costs are the costs that are independent of the sales volume. For example, design is a fixed cost. The costs of, let's say, manufacturing, the fabrication of each chip is a variable cost. The cost of shipping the chip is a variable cost. The cost of fabricating the masks for the fabrication of the chip is a non-recurring expense, because you do it once and you can use the same set of masks for the whole production. Of course, we need to make this consideration, because if we want to evaluate the total cost of one chip, typically you have to consider the recurring expense, so the variable cost for one chip, plus a fraction of the fixed cost, of course, which is, of course, the fixed cost divided by the number of chips that you can manufacture. Okay? So, this is important with reference to what we discussed before, because of course, depending on the number of chips that you need to fabricate for your particular application, the total cost of one chip can change a lot, and the type of solution that is less expensive, of course, can change a lot. If you consider what we indicated before, of course, the custom hardware solution is something that has a large fixed cost, because it is typically done only for one specific application. Okay, so it really depends on the number of chips that you need for that application. And for example, if the number of chips is very small because the application is very specific, the cost per single chip can be extremely high. On the other hand, of course, if we go to the other extreme, just to make the case, an embedded microprocessor, of course, an embedded microprocessor that is completely programmable can be used for a large number of applications, and therefore you are in a different situation. The number of chips that you can do with the same embedded processor can be extremely high, so the fixed cost have a small impact. On the other hand, the variable cost per chip can be pretty high, because typically when you buy an embedded microprocessor, the cost of a single chip is much higher than the fabrication cost of a similar performing custom hardware. So basically, again, to summarize this concept, considering the different trade-off between flexibility and efficiency, we also have to take into account that when you go down these different solutions, you have an increase of the variable costs because these single objects cost more and more for the fabrication. But of course, you can reduce the non-recurring costs because, of course, there can be many more chips in which a programmable piece of logic can be used. Okay, now let's look more in the details of what are the components of the recurring and non-recurring expenses. And so NRE means non-recurring expenses and RE means recurring expenses. So I mentioned the design costs are a non-recurring expense, so the time and the person months required for the design, of course that is a cost that can be pretty huge, especially for the teams that I mentioned of 1,000 people for a few months. Then you had to add the production equipment related to the specific chip. The production equipment related to the specific chip are, for example, the masks that you have, the masks for the lithography that, of course, are, let's say, have to be done for every specific chip design. Essentially, that's it. The recurring expenses are, in principle, a bit more complicated. Of course, one has to take into account different components. One has to take into account the cost of the die, and the cost of the die is the real cost of the processed piece of silicon on which you have the integrated circuit. Okay, so the die is the small rectangle of silicon on which you have the final integrated circuits. Then you have to add the cost of die test, and then you have to add the cost of packaging, of putting the die into a package and soldering everything together. Then the other important part is that then you have to divide this cost by the final test yield. The final test yield, of course, is a number which is smaller than 1, between 0 and 1, and it's basically the percentage of chips that after the test are actually working. Okay? So we already discussed this issue. This can be critical because, I mean, especially for very advanced processes, the final test yield can be pretty small at the beginning, and then typically when the process, let's say, is optimized during runs and runs, this test yield goes up to 80–90%. But at the beginning, it can be pretty low, 50% if the process is going well, but it can also go down to 20% if there are some issues. So, and of course, if you put it at the denominator, it increases a lot. A small yield at a final test can increase a lot the recurring costs. Okay, in practice, it means that you have to put in the trash a lot of the chips that you're fabricating, but after you have already paid for everything. Okay. Typically, sometimes you're able to do the test before the packaging, so you can maybe discard the cost of the packaging, but in principle, that is there, let's say in general terms. Now, in the cost of the die, of course, you need to consider the cost of the wafer divided by the dies per wafer, the number of dies that you have on each wafer, times the yield of each die. Again, this number, which is at the denominator, the number of dies per wafer, actually is the factor that is pushing, that has pushed in the last few years towards an increase of the diameter of the wafer. Okay. Now up to 300 millimeters. For a long time there have been, let's say, discussion of using larger wafer of 45 centimeters in diameter, but then it seems that there's a problem that the cost of processing each wafer is becoming higher than the increase you have in the number of dies. So there's no reduction in the cost per die. So these are all the components. Now, one thing that is actually interesting to consider is this die yield. Okay, so the die yield is the yield that you have on the dies before the package is done, and that is, of course, a function of different components. In particular, you can consider a couple of them. One of them is the number of defects that you have per area, let's say per square millimeter per area in general. And then an additional component is the area of the die, because the point is that typically a single large defect is sufficient to make the die not usable, and of course the larger the die, the easier is that you have the defect in the die. So there is in production an empirical formula for die yield, which is essentially this one. The die yield is the inverse of 1 plus the number of defects per unit area per the die area divided by half to the power of alpha minus 1 to the minus 1. And this alpha is equal to 3 for a modern CMOS process. So this is an empirical formula. It's not something that we can, let's say, demonstrate. It is something that can be justified, because of course this quantity, the number of defects per unit area that you have in the process times the die area, gives you the average number of defects that you have on a die. And the yield is strongly dependent of the number of defects that you have in the die area. So, for example, the expression goes like that. As a function of the die area, by putting 1 defect per centimeter squared, we can, and alpha equal to 3, we can see the die yield goes something like this, as a function of the area in centimeters squared. You see, for a small die, you can have a very high yield, but then as you increase the area, the yield can become pretty low. For example, if you have just 1 defect per centimeter squared, which is a very small number of defects, you see here, if you have 1 centimeter squared, the yield is already 40%. So you have a significant decrease. And this is actually the reason why we are not increasing that much the die area. So, as I mentioned already, in the last, let's say, 30-40 years, the die area has increased somewhat, but not that much. And the reason is this one. It's because the more you increase the die area, the more you are, let's say, decreasing the yield. The quality of a process is given by this number, the number of defects that you have per unit area. But then, of course, if you want to increase the area, you're strongly reducing the yield. And the other quantities are not that much let's say, changed by that, because of course when you increase the die area, you reduce the cost of dies per wafer, so you're increasing the cost of the die, and this is what you expect. Okay, you already expect that if you double the area of the die, you also double the cost. This is something that you expect, but it's worse than that, because when you increase the area of the die, you also decrease significantly the yield. So the cost goes up more than linearly with the area.